Okay, great. Thank you, Emily. Hi, everyone. Thank you so much for joining us tonight for this exciting webinar. Our guest this evening is Assil Halimi. He is a PhD candidate in the Nuclear Science and Engineering Department at MIT, and he's the co-president of the American Nuclear Society Student Section, also at MIT. He graduated from the University of Lyon, France in mathematics and economics in 2018 and has 2 engineer's degrees from places that I'm going to mispronounce because I don't speak French very well. One is a degree in electrical engineering from the Institut National de Science Appliquées and in nuclear engineering in 2019 from the Institut National des Sciences et Techniques Nucléaires. And before joining the graduate program at MIT, he worked as a core physics engineer at a company that operates Belgian nuclear power plants. And he's also interned at several organizations around the world in Africa, Europe, and the US, working on many different technology applications like aircraft, electric propulsion, oil and gas distribution, and turbine maintenance, and system design platforms and education. And I have been looking forward to this presentation for a while because as some of you who are on this call know, we give these presentations about climate and health. And when we get to the section at the end about the solutions, I always give a shout out to our engineering colleagues who are saving the world for us. But when I get to my one slide about nuclear engineering and science, I'm not really sure what I'm talking about. So I'm really looking forward to Mr. Halimi's presentation tonight. Thanks so much, everyone, for joining us. And please feel free to put questions in the chat as we go, and we'll call them out at the end. Or maybe I'll call on you and have you read your questions yourselves if you like. So thank you very much. Take it away.
Thank you. Thank you, Deborah. Thank you, Emily, for organizing these sessions. I think climate change is a multidimensional challenge, and you bringing the societal part and the technical part together is an important task. Thank you. I'm going to share my screen. I hope everyone can see my screen and can hear me well.
Yep.
Yeah, so the topic I wanted to talk about today is nuclear engineering and energy and how that related to climate change and sustainability. But just before starting, I wanted to make a disclaimer regarding the opinions expressed in this presentation represent only those of the presenter and not those of the organizations I work for or I represent, specifically MIT and the American Nuclear Society. So I'm going to start with the news. You probably see every day or regularly how we break new records in terms of temperatures measured around the globe. And here, the one I'm reporting is one of July 2023. And you can see that we have 1.2 degrees C above the baseline period. So when we say, let's limit climate change to 1.5, 2 degrees C, it's compared to a certain baseline period. And here it's represented as the period between 1950 and 1980. And sometimes we use the time period that is before the industrial revolution in order to talk about temperature increase induced by human activity. And so why do we care about this temperature of the globe? First, what we care about is not the temperature that we measure every day. And that's kind of this distinction between climate and weather. What we care about is the average temperature around the globe and how is that evolving. And Earth is located at a certain location in the solar system from the sun and receives a certain amount of heat. And it's located at this position where the heat flux is such that it is suitable for life to thrive. However, that's not enough. If we look at the moon, which is just next to Earth, and the moon does not have an atmosphere, the temperature at night is minus 208 Fahrenheit, and the temperature during the day is 250 degree Fahrenheit. So you need more than just the location. You actually need that thick layer around your planet in order to ensure that you have a temperature that is homogeneous and that is suitable for life, and more specifically human life. So I'm going to talk a little bit about how humans will change the composition of this layer of atmosphere that is around the surface of the Earth. And what we talk about is mostly is greenhouse effect, which is this ability of this atmosphere to trap the heat in the on Earth's surface. And it does that thanks to the property of some gases that we call greenhouse gases. And humans mostly emit carbon dioxide, which is one of these gases, but also emits methane, and you have nitrous oxide and F-gases. But you can see that in terms of the share, carbon dioxide represents about 3/4. And that's why that's our primary target. But we should not forget that about 1/4 of these greenhouse gas emissions are also contributing. And we should not consider solutions that will target reducing carbon dioxide and at the same time increasing other emissions. The second plot that I wanted to show is how do we split the emission of these greenhouse gases based on the different activities of humans. So we have electricity and heat production, about 1/4, agriculture, forestry, buildings, transportation, industry, and other energy uses. So that's kind of similarly shared between these different sectors. But if we look at each sector, the industry uses energy, transportation uses energy, buildings use energy in order to construct them. So if we look actually at what's the share of energy within all these sectors, it is about 3/4. And that's why when we try to look at greenhouse gas emissions, we look at energy as the first target because it represents these 3/4 of all emissions. Now, I wanted to show is how the greenhouse gas emissions are distributed between countries. So we have, this is 2014 data. We have China about 30%, United States 15%, the EU about 10%, and then India and other countries, other developing countries. And you can see that just targeting or trying to solve the problem by reducing emissions of one country is not enough. And more, we have to emphasize also the fact that developing countries will occupy a larger share of this pie. And therefore, trying to figure out a solution for climate change will certainly require global cooperation between several countries and not just one. Now I wanted to clarify some of the concepts and dynamics related to energy. And first plot that I show here is the decomposition of the sources of energy, or what we call the primary energy. And you can see that first we can get petroleum, natural gas, renewable energy, coal, and nuclear straight from nature. And then on the right side, you can see the different end use that actually represent how do we see energy in our everyday life. We see it as transportation, we see it as industry, we see it as applications in our residential activities or commercial activities. Sometimes some of this energy comes straight from the primary energy. Example, you take the gas from petroleum that is refined, you take that and then fill your tank and drive your car. But in some situations, you don't use energy straight from the source, or you don't use the primary energy, but you go through what we call an energy vector, like electricity. And therefore, what you have to question is where does your electricity come from, or what's the primary source of that electricity? So in some cases, if your electricity is generated by natural gas or petroleum, then your carbon emissions are still high. If it is generated by nuclear or renewable energy, in that case, your electricity is clean, and you can drive your electric car knowing that the effect on the environment is not that bad. The second plot that I wanted to show here on the right is how this primary energy I was talking about, it had evolved since the 50s in the US, more specifically its production in the US since the 50s. And you see here the decomposition of this primary energy. We have coal in blue, we have natural gas, crude oil, natural gas plant liquids. And these, compared to nuclear and renewables, which includes hydropower, these carbonized sources represent roughly 70 to 70% of the total in the US. And the challenge of the coming 30 years is to bring this share to zero, or to some value that is around zero if we count for some carbon sinks or carbon capture. But we know that the size of the decrease is significant, and we have to bring it to a much lower levels. And the dynamics that have to take place are way different than what we have seen in the past. Now, I wanted to talk about nuclear energy more specifically and clarify some of the concepts. So we get energy from nuclear starting from three different reactions. The first one is fission, where you take a large heavy atom like uranium-235 and then use a neutron and you split it into two fission products. And in that process, you release some binding energy. Fusion is kind of the reverse. You take two light elements like deuterium and tritium, and then you fuse them to create a heavier element. And in that process, similarly, you release binding energy. And then the third way of generating energy is to use the radioactive decay of some unstable elements like radium here that decays to radon. And in that process, it releases some small particle like a positron or an electron or an alpha particle. Another feature of nuclear energy is the fact that it has a very high energy density compared to other energy sources. And you can see here this funny cartoon that shows how log scales are needed actually in order to compare such discrepancy in terms of energy density. This is practically related to the four fundamental forces of nature, and the nuclear fission, for example, is related to the strong nuclear force compared to other forces that are weaker, like gravity, like electromagnetism, or the weak nuclear force. So what does that mean practically? If we take a power plant that generates 1 gigawatt electric of power or 1,000 megawatt electric of power, if you want to use coal, you will have to use about 6,700 tons per day of coal in order to operate that plant. For natural gas, you will have to use 3,700 tons per day in order to operate the same the power plant with the same power output. And then for nuclear fission, all you need is 3 kilograms of fuel per day in order to generate the same amount of power. So that's kind of gives you a practical idea of how this energy density comes to play. Now, our first topic was climate change. And so in this plot, I wanted to show how the different energy generation tools that we have compare in terms of CO2 emissions. So here on the y-axis, you can see grams of CO2 per unit of energy called kilowatt hour. And our fossil sources like coal, biomass, co-firing, natural gas have a high level of CO2 per unit of energy produced. And then if we look at other sources like renewables, nuclear, this value is low. We're talking about 12 grams CO2 per kilowatt hour. And this plot takes into account all the CO2 emissions, not just during operation, but you have to consider how much you emit during the construction, during the mining, during the transport, during the commissioning, and the waste disposal. Also, you can see that we talk always about low carbon sources. There are no such zero carbon sources because you have somehow in the life cycle to go through some process that will emit some CO2. Now, I will talk about the material usage and how much, in order to build or construct your power plant, how much material you have to mine in nature and therefore disturb the ecosystems in order to construct your power plant. You can see for some of the renewable sources like solar PV, like hydro, like wind, you have to use a consequential amount of concrete, cement, or steel. Here the y-axis represents the amount of material per unit of energy. And so by that same metric, if you look at thermal power plants like coal, natural gas, and nuclear, they have such a high energy density that their power plant will not consume as much concrete, steel, and glass, etc. But that's not a full story, because if you look at renewable sources, they don't consume fuel. Practically, the sun is always here. The wind is not always, but most of the time here. The wind is here too. But for our thermal plants, you have to add the fuel, and you have to mine that fuel from nature. So what I added here is how much coal you need to mine in order to give the same unit of energy here. And you can see we have plus 280,000 ton per terawatt hour. That's actually very high, even higher than the upper limit of this scale. So I just added an arrow here. Same thing for natural gas, 160,000 ton per terawatt hour. And that's also very high compared to the limit of this plot. And then for nuclear, the value is 125 ton per terawatt hour. So if we take into account how much material you have to mine, either to construct the power plant or to operate the power plant as fuel, nuclear comes out to have the lowest value. Now, another factor that is important in order to compare different sources of generating electricity, and here I just simply took three major sources: nuclear, solar, and wind. And here, this is kind of the performance in space and time, or how much space does it take to construct a solar plant, a wind power plant, or nuclear power plant. And in order to measure that, we talk about the power density per area, or how much megawatt electric can you generate given the square kilometer of area. And you can see for nuclear is about 2,260 megawatt electric per square kilometer. For solar and wind, these values are much lower. The energy density is much lower. So you have to use a lot of space. And this can be a problem if we look at countries that do not have as much space for solar. That can be a concern. And same thing for wind. To a lower extent, if we consider the fact that around those wind turbines we can have some activities, but a high number of them are not actually allowed to take place around the wind turbines. The second factor is the capacity factor, or how much during a year you're producing electricity. And if you look at nuclear, 90% of the time, the power plant is generating electricity during the day, during the night. The only time it has to shut down is to do the refueling or the maintenance. For solar and wind, the capacity factor is lower, less than 30% for solar and less than 40% for wind. And that this is inherently due to the fact that the sun is not always there and the wind is not always there. Now, I wanted to talk a little bit about waste. There is clearly concern when we look at the public opinions here in the US and in the world related to the waste that is generated by nuclear power. And this is a figure that shows total projected global waste by 2050. It was produced by the International Renewable Energy Agency. You can see that solar and wind have some elements that will be left in the environment that are toxic, that are carcinogenic, and therefore we have, compared to nuclear, we have also a source of energy that generate this waste. And this is a high motivation for these two sources to consider recycling, which will inevitably increase the cost. But if we just consider the business model that is deployed today, solar and wind will have much higher waste and therefore impact on the ecosystems. So nuclear, I can see here barely see its share in terms of generated waste. And one interesting example that we probably will remember after this presentation is if you take one person lifetime spent fuel volume from nuclear power plant, if this person would have used only energy generated by nuclear, this amount of waste will be comparable to the size of a glass. And that's kind of the size of the waste that you generate if you only use nuclear. Now, this plot shows the fatalities related to operating power plants. And this is not a very cheerful way of looking at how different sources produce energy. We have to take into account this in order to compare different technologies. And you can see that for coal, and more specifically in China, the fatalities are much higher. This is due to respiratory diseases that are induced by dust and fine particles that are generated by coal plants. And then to a lesser extent, we have oil, biofuel, coal, other fossil fuels. And if we look at renewables and nuclear, we have the lowest values. This number here includes the accident of Chernobyl, which reported deaths related to the accident. Another important aspect related to nuclear is radioactivity. We worry a lot about how much dose we get, this relationship with getting exposed to radioactivity. We have to remember that we are daily exposed to radioactivity. And the way we measure this is using a unit called millisieverts. And what I'm reporting here is the annual effective dose for different professions. And you can see here for medical, aviation, nuclear power, industry, education, etc. And this number is actually not the highest for nuclear workers. The people who receive on average the highest doses are the personnel working for aviation. And keep in mind these figures. If you look at some locations around Earth that are naturally radioactive, like Denver in Colorado, we have annually on average 12.4 millisieverts received by the people living in the area. Ramsar in Iran, some people in that area receive doses as high as 260 millisievert annually. And that was not correlated to any increase of cancer around the area. The ISS, or the International Space Station, people going there, they will get 200 up to 400 millisievert. And I just reported here the recommendations that are recommended by the International Commission for Radiation Protection. For the general public, it's 1 millisievert annually. And then for nuclear workers, it's maximum 20 millisievert annually. Now, I want to talk a little bit beyond the energy applications, other applications of nuclear science. And so for energy, we also, in addition to generating electricity, we can generate hydrogen, district heating. It is used for healthcare, for diagnosis, therapy, sterilization, insect control. It is used for transportation, particularly for nuclear-powered ships, in space missions, more specifically space missions that go beyond the Mars orbit and cannot be powered for longer times by sun. Agriculture, we use it for plant mutation, we use it for fertilizers labeling, for food irradiation, and then for the industry, we have also plenty of uses: tracers, instrumentation, carbon dating, desalination, and consumer products. Consumer products, you can cite one, smoke detectors. Smoke detectors use an element called americium-241, and that element is actually a byproduct of plutonium-241 that is generated in nuclear power stations. Now a little bit of history, and I wanted to talk about major accidents that happened during the operation of commercial power plants. And so the first major one occurred in the US, Pennsylvania, in March 1979, and the TMI Unit 2 that had experienced a partial core meltdown, and that started from the event of losing a feed water pump. And then afterwards, the progression of the accident had been allowed by misinterpretation of instrumentation signals, lack of understanding of accident phenomenology, and other factors. So after that, so the operator had managed to control the meltdown and restore the cooling in the core. However, some radioactivity was released beyond the vessel and beyond the reactor containment out to the atmosphere. And so just to give you an idea of how much people had received during that event, the people who were around the area had received an average of 14 microsievert. And if you go and get a chest X-ray, you will have 32 microsievert. And despite that, we had a spontaneous evacuation of 150,000 people from the area. The second accident occurred about 7 years after TMI accident and in the former Soviet Union. And this was due to a misconducted operator test. Clearly, the operators didn't have any idea of how the physics of the reactor was evolving during the accident. And in addition to that, the design, who is, by the way, very different than the designs of nuclear reactors that we build today or we build in the West or operate in the West. And that design had some weaknesses that made the situation worse and created this power surge that led to a steam explosion that destroyed the reactor enclosure for this plant. And the plant had the moderator for this plant was graphite, and that graphite was burning for days. So many people had died trying to extinguish that fire. The last accident, or the last major accident, occurred in March 2011 in Japan, in its eastern coast. And this occurred after an unprecedented earthquake that occurred under the ocean. And that unprecedented earthquake, I think magnitude 9.1, had generated a tsunami wave that was beyond the design of the seawall that was protecting the power plant. So water had came into the plant and flood parts of the plant, including the building where the diesel generators, emergency diesel generators were located. Therefore, those diesel generators were not able to provide a heat sink to the plant, and we had 3 core meltdowns and 4 hydrogen explosions in the power plant. We had radioactive elements that were released in the environment. And to note here, there is no direct death that had been reported from the accident. Actually, most of the people who died in the Fukushima disaster were related either to the tsunami itself or to the evacuation of over 160,000 people that lived around the area. Now back to the present, and I'm going to talk a little bit about the situation of nuclear today in the US, more specifically. And we see today a growing consensus on the role of nuclear energy in fighting climate change. And actually, a lot of figures are actually supporting nuclear. We have Bill Gates, who publicly supports nuclear and has a startup called TerraPower that is developing an advanced reactor that we'll show in a few slides from now. Last year, or I think this year, we've seen the release of Nuclear Now, which is a documentary by Oliver Stone, who worked on deconstructing some of the myths that were related to nuclear and the misperception from public. And politically speaking, we see an increasing support from both parties in the U.S. during the last few years, and that kind of translates into some of the policies that we are seeing today. The Inflation Reduction Act has several provisions for keeping the current nuclear power plants operating, but also investing on deploying new advanced reactors in the US. And then I just put some statement of figures, public figures in the Silicon Valley who either support or invest some of their money in nuclear startups. Probably this is the most technical slide. I will just talk about what's going on in nuclear power plant, kind of remove the dust on some of the ideas that probably can have around what's going on in a nuclear plant. So in the world, most of the power plants, we have about 460 commercial reactors. 90% of them are either what we call PWRs, or pressurized water reactors, or BWRs, boiling water reactors. And they are shown, I show them here, and the way they operate is you have your fuel that is located here. This is a PWR, and then you pump water that will cool your fuel, and then take the hot water to heat another water tank that is called a steam generator that will generate the steam, which turns the turbine, and then turns the generator to produce electricity. And the other design, which is the boiling water reactor, we pump water directly to the core and then generate the steam in the core, and then send the steam directly to the turbine, turn the turbine, turn the generator, and you have electricity. The difference between the two, you can see that it's this component. It's called the steam generator. In one case, we generate steam in this component, and in the other case, we generate steam directly in the core. So both these types of reactors are used for mostly generating electricity, but we have cases where they have been used for district heating, for desalination, and for isotope production for different uses. And now talking about today and who's building reactors, we see that mostly Asian countries, and China is leading the race with constructing several reactors, and they have plans for tens of reactors in the coming years. And same thing for India, Republic of Korea. However, in the US, we've been building only 2 nuclear reactors recently, and they will, I think one started operating this year, and one will start by the 2024. These are the 2 units at Vogel in Georgia. And these units, we're talking about traditional large reactors, and the US has been having a hard time meeting the budget and the schedule regarding these units. And that's why we don't see many orders for traditional large reactors in the US. And so I'm going to talk a little bit about this cost problem, and I will start by giving an example. This is a natural gas power plant. Its output is 1.6 gigawatt electric. It takes 2.5 years to construct, and about 1.5 billion investment to build. And on the opposite side, we have a nuclear plant, Georgia Power, and it takes for about a little bit more of power. It takes 10 years to construct, and $32 billion as an investment. Of course, for nuclear compared to natural gas, the fuel is much cheaper. So we can allow ourselves to have a plant that is 3x, 4x more expensive. However, if you have a project of this size, it kind of stops the investors, stop the utilities from taking such a huge risk when the size of a project is approximately the size of the company itself. So these are several reasons why these reactors are not going well in the US. So the construction has started with little design completed. We have lost experience and non-consolidated supply chain because we didn't build reactors in years here in the US. The regulatory process that is averse to design changes during construction. And it has to be noted that the Fukushima accident occurred and had implied some updates regarding the design, so that kind of delayed further the construction of this plant. And an aggravating factor, which is labor productivity, that had decreased significantly in the West, where we've seen more productivity in factories, but less and less productivity in construction sites. Now I'm going to talk about the solutions, or what we think are the solutions. And in the US, the approach is to build smaller plants. When you build a smaller plant, naturally your construction time will decrease. You will control the engineering and the licensing uncertainty by having this small project compared to a mega project with a high risk. And then you reduce the management burden that is related to the fact that you have a smaller labor force, and therefore you can have better control of what's going on site. But also the idea here is to shift some of the labor from the site to the factories. So some of the components and the systems, instead of doing the welding or the assembly on site, we'll do it in factories, where you have a better control of the uncertainty of the different manufacturing processes. Of course, there's no free lunch, and when you go from a large plant to a smaller plant, you have to sacrifice some of the economies of scale. And the economies of scale will touch your capital cost, will touch your operation maintenance cost, and to a lesser extent, your fuel cost. And part of the challenge of succeeding in making this leap in terms of designing new power plants is to innovate in terms of systems and designing the power plant in such a way that you mitigate the effect of economies of scale, and you enhance the certainty and minimize the risk related to the project. That's kind of a little bit related to what I do in my PhD thesis. Try to look at these different trade-offs and see how we can improve the design of these small reactors. So speaking of which, light water reactors, so these are some of the examples of startups that are developing in the US, but also around the world. You have NuScale Power, which construct this module, which is a pressurized water reactor. I don't know if you remember the pressurized water reactor that I showed earlier, but kind of compacted in a single module. And so you build this module in a factory, and then you move it on site where you simply have the reactor building and different other components, where most of the work is done on the factory. Similarly, you have Holtec with their SMR 160, which is similar pressurized water reactor. We have a boiling water reactor by GE, which is a 300 megawatt electric output. And then if you go outside of the US, we have companies like EDF in France developing their own small modular reactors. In the UK, we have Rolls-Royce developing their own small modular reactor. And in China, they have their own model of a smaller size reactor. Now, in terms of reactors, we don't have only water-cooled, but we have different design types that use to cool the core or to cool the fuel. They use gas or liquid metals. And some of these examples, here we have the HTR-PM in China. There is a pebble bed reactor cooled by gas, and it has finished construction recently. In the US, we have X-Energy developing a similar concept, pebble bed reactor. We have Keros Power, similarly, and Natrium, which is the Bill Gates company, that is developing also a sodium-cooled reactor with molten salt tanks in order to modulate power. And in Boston, we have Boston Atomics, which is a startup that came out of our department and is working on a concept where you have a horizontal constructed reactor in order to improve the productivity on site for constructing such reactors. And then you saw on the previous slide, most of the reactors were on the size of few hundred megawatt electric. Microreactors take the concept of making the reactor smaller even further. And here we're talking 1, 2, maximum 50 megawatt electric reactors, and they are very, very small. And to give you an idea, this is a comparison of 10 megawatt to a wind turbine and a microreactor with the same power output, or similarly a solar farm compared to a 10 megawatt microreactor. So here you can see the power density at play in deploying such reactors. And so we have a certain number of startups here, mostly here in the US, that develop these concepts. And now to end this presentation, I wanted to give you some takeaway messages. At first, back to our climate change. So meeting the goals, when we talk about 1.5, 2 degrees in the next 30 years, implies having a fundamental change in the energy sources mix. And the transition has to be made from carbon-based sources to low-carbon technologies. Nuclear energy technology positions itself among the few proven, scalable, and sustainable options to achieve economy decarbonization in the next 30 years. And building traditional reactors, Asia has been doing it successfully in the past few years. However, in the West, we're having a hard time replicating the successes of the past. And the new path here is to consider advanced small-sized reactors that hold a promise of reducing the cost and construction duration, and enabling this fast-paced transition that we need in the next decades. And finally, opinions regarding nuclear power are shifting to strongly support maintaining the existing fleet, constructing new nuclear power plant, and investing in advanced reactors. And to finish, I just wanted to highlight this plot that shows the evolution of average life expectancy compared to how much energy we use in different countries in the world. And we have a fair correlation here that shows that your life expectancy would increase. And this increase is more significant at the beginning here, where you have the first unit of energy use in order to increase life expectancy, but also lifestyle. And what we are facing now, when we talk about removing fossil fuels, removing those energy sources that we have, is going backwards on this curve. And nuclear energy is offering us a way to keep our energy use at a significant or at a decent level, and at the same time keeping our lifestyle and life expectancies. And with that, I will end here. I will be happy to take questions.
Thank you so much. Would you like to stop sharing your screen so we can see you a little bit better? Excellent. That was a really fantastic presentation. Thank you so much. You made a really good explanation of the technology and all of the reasons why we are going to need to use nuclear energy to do something about climate change. And I feel like I understand how nuclear reactor works a lot better than I did in the past. So we've got a couple of comments in the chat, and we also have some questions. And if anybody has any other questions and they want to raise their hand, that would be fine too. But I'll start by reading some of the questions in the chat. So we had one question, which I was wondering about as well. Why did Denver and that particular town in Iran have such high number of such a high radiation exposure?
Yeah, so that's related for Denver to two factors. So we have the altitude. Actually, Colorado is in terms of altitude, one of the highest in the US, and that gets you more exposure to radiation, cosmic radiation. That's one factor. And the second factor is the type of rocks in the area that is granitic. And that type of rock contains radon, which is an alpha emitter. And so whether you build the houses using materials from the area, using the rocks from the area, will get you exposed more to radiation.
Excellent. Okay, and it looks like Kathleen has her hand raised. Kathleen, if you want to unmute, you could ask your question.
Sorry about that. Took me a second. So I'm curious. So first of all, very impressed. I went from knowing like nothing to a little bit, which was a lot more than I knew. So thank you so much. And it is a good story for why we should think about nuclear. I'm wondering, when people worry about nuclear, are there things? So for instance, I was just trying to think about what would make me really scared. So I wonder if, for instance, terrorists would have a lot easier ability to affect that than a big solar array or whatever. But not only that, I'm just wondering, yes, about that, but are there other things that you haven't mentioned that we should be worried about or think about, actually?
Yeah, there are several concerns. I talk about the waste. There are concerns related to proliferation, and we sometimes often make the association between the military use of uranium and the civil use of uranium. And it turns out that we have standards for decades now. The fuel that we have in our nuclear reactors is much, much different than what you need to get a bomb. And so we have standards that are enforced by the IAEA, the International Agency for Atomic Energy. And so we have also inspectors by this agency that go to all different power plants. But the bottom idea here is to say that the fuel, we design reactors, they use fuel that has an enrichment that is so much low that is they would need the same amount of effort to turn uranium you find on the ground somewhere to a bomb than the uranium you find in the plant to a bomb. So yeah, there are some by design, the nuclear reactors prevents the proliferation. Of course, the risk is not zero, but it's similar, as I said, to just getting uranium from outside and mining it and doing the same thing. I'm thinking if there are other. So yeah, the waste actually is a big concern, especially here in the US, and as I showed, the waste amount is lower. We have today a technology of managing the waste, where we put the fuel in fuel casks. We have questions that are related to, are we taking care of that waste? And the answer is yes, of course. And then we have so for some of the waste, there is what we call high activity, long life waste that stays there for thousands of years. We have two solutions. So for the current reactors, the experts of the sector agree that putting that waste under geological layers that have proven to be stable for hundreds of thousands of years is the solution. And the second part of the solution is we can change the reactor designs themselves so they can produce much less waste. And that's part of the generation 4 or some of the reactors that are not water cooled that I showed earlier. And those reactors actually transmute the heavy elements that are much more radioactive and that stay longer in nature. And so, yeah, twofold answering this waste issue.
Excellent. Okay, so I have another question here about whether the reactors that are cooled by liquid metals are inherently safer from meltdown than traditional reactors.
Yes, we have experiments that we had in the US during the 80s, what we called a reactor called the EBR-2 in Idaho that experimented using sodium to cool the fuel. And the idea there is to design a reactor so that in case the temperature will increase, in case we lose control. So they actually did an experiment where they tried all the worst configuration possible, and then they left the control room and then let the reactor evolve and try to see if it will melt down, and it didn't. Because by design, the reactor, when it gets hotter, the reaction will decrease. The fission will decrease. So we'll have less fission, so it gets cooler and kind of self-stabilize itself by design. So yeah, that idea is correct.
Okay, I have so many questions here, so I'll just keep picking some out. Okay, so someone says a lot of people think fusion will be the savior of the human race. Is that really likely to be safer or cheaper than fission-based energy? What do you think?
Yeah, that's a great question. I talk with colleagues about this, and yes, that's an option. That's an option that we have in order to fight for climate change. I can't tell you if it's going to be the cheapest option. I can't tell you if it's going to be the dominant technology. That will depend on many factors. One factor, it depends on how much money we invest in order to accelerate the deployment of such technology, because we know by physics principles that we can generate electricity using fusion. Secondly, policy has to be favorable, and the regulatory system has to be in favor of deploying such technology. And the third aspect is people working in the field. These are the people who are going to make it cheaper or not. It's actually my colleagues. I work on fission, but my colleagues work on fusion. And if they work hard enough, they can make a machine that is much cheaper or not. So these are the factors. I can't tell what's the outcome.
Okay, thank you. And now we have two people who have asked a question. I don't know if you can answer it or not, but we have the Seabrook power plant, nuclear power plant in New Hampshire that gives us a lot of our energy. So do you have any idea how long that can keep operating safely?
Yeah, so just to clarify, the NRC, which is Nuclear Regulatory Commission here in the US, will not authorize operating any nuclear power plant if it's not safe. Just to clarify that point. Then here in the US, we are extending the life of nuclear power plants. When we say extending the life of nuclear power plant, it does not mean that we keep all the old machines and the components. Most of them are changed. We change them. We make updates to the plant. What we don't change is the reactor building and the reactor vessel. These are the parts that are sensitive, and it would take so much money that you rather build a new plant instead. And so most of the work that is done is to make sure that the reactor building and the reactor vessel will safely operate for an extension of 10 years, 20 years. Here in the US, we have extended several reactors to 60 years. We talk about extending the operation of some reactors to 80 years. And this is an important factor if we talk about sustainability. If we look at other power plants, coal, natural gas, usually the lifetime is 40 years. You have to build a new one. You have to mine all those elements from the environment in order to construct a new reactor. Whereas for a nuclear power plant, it is there for almost 100 years. So you don't have to build it again.
Excellent. So we're running out of time. I'm going to just read one more question here, and I don't know if you can help us with this, but the question is, why is it that there's more support for nuclear energy from Republicans than Democrats, and how can we change that?
I can't tell. I don't work in the field of analyzing the political views and how is that related. I'm happy to see that both parties today are working together and recognizing the fact that that nuclear is an answer not only for climate change, energy transition, but also for energy security, which is a topic that is getting more and more important today, given what's going on around the world and the supply of oil and gas.
Excellent. And I hate to do this, but I'm going to ask one more question because I just saw this one in the chat. And it says, as I understand it, the newer generation reactors can use previously depleted uranium. Is that true? And can you elaborate on that?
Yeah, that is correct. Some of them are planning to buy existing fuel. Actually, in France, they did it and they continue to do it. They reuse the same fuel from some plants to build a new fuel called mixed oxide fuel, where they mix some of the waste fuel, those from not older plant, but plants that operate with fresh fuel, to operate with that fuel. So we call this recycling. We have multi-recycling. And then generation 4 will take that concept further to kind of use more and more of that waste, and therefore reduce the final impact on the environment.
Well, thank you so much. This was really fantastic.
My pleasure.